Section 2. Detectors for GC. The detector is the measuring component of the GC system. In some cases, the detector measures everything that comes out of the column, regardless of what it is. This would describe a detector with low selectivity or specificity. In other cases, the detector is only sensitive to certain chemicals and will show no response to others. Fluorescence and absorbance detectors fall in this category. Finally, there are those detectors that add a step of selection or exclusion prior to the actual measurement, such as the mass spectrometry detector. In the flame ionization detector, the effluent from the column is mixed with hydrogen and air and ignited. Ions and electrons are produced as the organic compounds burn. These conduct electricity through the flame. A large electrical potential is applied at the burner tip, and a collector electrode is located above the flame. The current resulting from the pyrolysis of any and all organic compounds is measured. One important advantage of FID is that it is mass sensitive rather than concentration sensitive. This gives the advantage that changes in mobile phase flow rate do not affect the detector's response. The FID is a useful general detector for the analysis of organic compounds. It has high sensitivity, a large linear response range, and low noise. It's also robust and easy to use for almost all organic compounds which have a CH or CN structure. In the electron capture detector, the nitrogen carrier gas is ionized by a beta ray, and the electrons released are captured by the electrophilic compounds that result in a negative ion. These ions are conductive, and the change in the current produces a peak. This detector is used in food safety for pesticides and environmental contaminants. The flame photometric detectors, FPD, are good for sulfur, phosphorus, tin, and a few other elements that burn to specific colors or wavelengths in a hydrogen flame. FPD is highly sensitive and selective, which makes it well suited for food contaminants, and there are usually low concentrations. In addition, it's a very stable detector. It is especially useful in the food safety laboratory to measure phosphorus pesticides. The flame thermionic detector is a highly sensitive and selective detector for organic nitrogen compounds and inorganic and organic phosphorus compounds. It's also known as a nitrogen phosphorus detector, NPD, because it detects nitrogen and phosphorus compounds. Its selectivity to phosphorus compounds is lower than FPD. The main applications of FTD include the analysis of drugs, nitrogen pesticides, and phosphorus pesticides. The mass spectrometry component of a GCMS system is the same as described in Module 4 dedicated to HPLC and in the upcoming Module 6. Briefly, a quadrupole maintained under high vacuum uses radio frequency and polarity switches to guide ions of a particular mass-to-charge ratio to a detector. This type of detector is highly selective because it will only allow one mass-to-charge ratio through, but we must bear in mind that more than one chemical compound may produce ions of this mass-to-charge ratio. Combining two quadrupoles and a collision chamber between them increases the selectivity even more, which is why this combination is considered to provide sufficient information for confirmation of identity. The very small size of the sample effectively making it through the GC column sometimes justifies the use of a concentration step, such as an ion trap, which will be discussed in Module 6. Gas chromatography has a solid place in the food safety laboratory for a number of reasons. While the absence of structural information limits the confirmation capabilities with older detectors to just matching retention times with multiple columns, mass spectrometry really bridges this gap. Obviously, the approximately 50 pesticides that are not amenable to LC analysis could be justification enough. But some older, mostly phased out pesticides, such as organochlorides and organophosphates, still require testing because they are either still registered for use in some countries or because they are found in the environment. And these are also not doable on HPLC. Some pesticides can be brought into HPLC-MS methods, but challenges still exist for very low concentrations. The combination of GC with mass spectrometry has expanded the scope of use to confirmation analysis in a single method. This has contributed to make GC highly desirable again in the food safety laboratory, especially for pesticide residue analysis. When the scope of the laboratory more broadly covers food analysis, the strength of GC for oil analysis and its powerful detection and confirmation of pesticide residues give it even more value for a lower cost than the liquid chromatography equivalent. The typical sources used for mass spectrometry following GC separation are electron impact and chemical ionization. Electron ionization, formerly known as electron impact ionization, is a hard ionization technique. A metal filament is heated, which produces highly energetic electrons. These electrons meet the analytes from the GC in a chamber filled with a gas, usually methane, that slows down the highly energetic electrons. When they meet, the remaining high level of energy causes a fragmentation of the analyte molecules. The first fragment is usually one where electrons are knocked off the analyte, but many smaller fragments are generated as well. It is the pattern of fragmentation, a highly reproducible process, that enables the identification of the compound. Chemical ionization is a soft ionization like electrospray in LCMS. In this source, a gas is ionized, usually methane gas, by an electron beam. When the ionized gas meets the analyte, a hydrogen molecule is transferred, which produces a quasi-molecular ion, an NH+, and some other ions in much smaller quantity. This is the positive mode of chemical ionization. Its advantage is that almost all analytes compatible with GC are compatible with positive CI. Negative CI is more selective in the sense that not all analytes will produce a stable negative quasi-molecular ion. It is very effective with environmental contaminants such as PCBs and fire retardants, as well as pesticides. The gas chromatograph is an important instrument in the food safety laboratory because equipped with appropriate detectors, it enables the analysis of a large number of semi-volatile compounds for which regulations exist. Liquid chromatography and gas chromatography are complementary techniques in the sense that they target molecules that are non-volatile for LC and semi-volatile or volatile for GC. The selection of the detector is critical, and as described in this module, many detectors exist that are suitable for specific chemical contaminants of food. However, mass spectrometry in the form of a single or tandem quadrupole is playing an increasingly important role for the identification and quantification of a wide variety of chemical contaminants. However, the high cost of this type of detector, the higher cost of maintenance, and most importantly, the specialized workforce that is hard to find, mean that there will still be a need for other detectors for many years to come. Many people have contributed slides, have contributed ideas, and have reviewed various parts of this module, and for that, I'm forever grateful.